Welcome back. We just completed the proof of the open mapping theorem, stating that in Banach spaces, if you take a bounded linear transformation between those two Banach spaces, x and y, say, then that guy is going to be an open map. So it's going to map open sets in X to open sets in the codomain Y. Now, an important corollary of this one, which will prepare immediately the next big theorem in the section, namely the inverse mapping theorem, is written here. I call it itself a theorem. So if you have a bounded linear transformation between two Banach spaces and that guy is injective, assuming that it has a closed range, then in a sense t is bounded away from 0 in this fashion here, right? So there exists positive epsilon, so that the norm of the image of x is always at least epsilon times the norm of x. So that's why when x is positive, you're always going to be bounded away from 0, right? So that's the first thing that we'll prove now. It's a consequence of the open mapping theorem. Okay, so how to do it? Well, for the open mapping theorem, we need something surjective, right? So if y hat is the range of t, okay, then remember the range is closed, so that makes it then itself a Banach space that I can equip with the original norm on y, and this guy is a Banach space. And t, whose codomain I now restrict to the range, is obviously onto, is surjective. Okay, hence, by the open mapping theorem, that guy is going to map open stuff to open stuff. So by the open mapping theorem, there exists epsilon positive, so that, well, for instance, that ball of radius 1 in X space is open. The open mapping theorem says this is going to be mapped to something open, so I can squeeze something open in there, but this is in the, well, in the range, in the space y hat, right? Yeah. So what does this mean? Thus, we have, let's give some freedom here for any delta between 0, 1. So epsilon 1 minus delta over txy, tx, x in x. This guy is going to be sitting inside b epsilon y hat 0. Remember, this ball here on the left is the ball in the range of t. That's how the y hat is defined, right? So and that's why I'm creating here an element in the range, right? So this is clearly in the range, t of x, and all this stuff does here up front is it scales it, right? So the ratio tx over the norm tx is obviously, you know, at most equal to 1. And then that factor 1 you scale by epsilon, because you gotta be in a, well, ball of radius epsilon. And then this little delta there, this gives you some more freedom, right? Delta is away from 0 and delta is away from 1. So epsilon times 1 minus delta is actually strictly less than epsilon. So certainly this inclusion here is correct. Where up here this is a hat. And that ball is in, well, t b1x0, right? That's what we already know because of the open mapping theorem. Yeah, but now we are kind of done, because you just have to write out now this here contained in that. But remember, you're working with an injective map, so that can only happen if that green bubble here, I'm avoiding the t because I have to go to the pre-image. I'm using injectivity is contained in that green bubble here, right? That's injectivity, right? So this green thing on the left is contained in the green thing on the right, but that's a ball of radius 1, so that's just telling me that the green bubble on the left in X norm cannot exceed 1, right? Since T is injective, therefore, well, what I just said in words, epsilon 1 minus delta Txy x in X norms, this is a small x, that was the green bubble, is strictly less than 1, right? And that is precisely giving me what I want. Just do the algebra, Txy epsilon 1 minus delta xx. Okay? And that is what's written up there in the theorem. The epsilon here and the epsilon down there, they are different, but that's why I have here the 1 minus delta. Okay, so I can push delta equals to 0, and then I will get the strict inequality with equality included and epsilon being redefined. Okay, so this is the claim. All right. Now that we have this, now we will be able to prove this big guy up here, the inverse mapping theorem, which is mighty important, going to be very useful in the upcoming chapter. So if you have a continuous linear bijection, and remember I said in general, for that thing to be invertible, it's not just going to be enough to be, well, continuous and bijective, because the inverse might be unbounded. And we had an example earlier on where that happened. And back then I said, well, much later we will understand why in that example the inverse is not bounded. And the thing was, if you remember that example, this was, I think, identity map between two sequence spaces, but one sequence space was equipped with a norm in which it is not complete. That is to say, one of those guys in the example was not a Banach space. And that's why it fell through, because this theorem says if they are both Banach spaces and you have a continuous linear bijection, then the inverse is automatically bounded. And here this is, of course, equivalent to being continuous, right? That's why you get this for free. If you work with bounded linear transformations between Banach spaces, not normed linear spaces, you need the completeness. We had an example why you need the completeness. But if you have it, then the bijection is automatically going to have a bounded inverse, aka a continuous inverse. All right, and this is easy to prove now by the last theorem. So remember the last theorem, maybe I'll write it in yellow. There was something injective, and the range was closed, and we were able to have this guy for all x in x, and so the proof, well, the proof was you restrict yourself to the range, which is then a Banach space, but here you get this for free because the target space is already a Banach space, right? So now the only thing that you have to do is apply this yellow stuff, but for x being the inverse of y, which exists, so you substitute it in the yellow part up there. What you have on the left is little y in y norm, epsilon, and on the right you have t minus 1x in x norm. And that's precisely the boundedness of the inverse, right? All that you have to do is you have to move this constant here to the right, to the left, if you read it from left to right, and then you have it, right? Which shows t minus 1 in L xy. All right? So you have this. Very nice, very nice, very nice. Good. That's the inverse mapping theorem. That's going to be very helpful, and in part explains why in the last chapter of this course we are only going to work in Banach spaces and actually most of the time in Hilbert spaces, because we want to exploit the inverse mapping theorem. Okay, a few more corollaries that come out of what we just did. So this inverse mapping theorem is a corollary to the open mapping theorem because it relies on the theorem that we proved before it, and that is a corollary to the open mapping theorem. Now, a corollary to the inverse mapping theorem, and hence corollary to the open mapping theorem, is the so-called norm equivalence. So remember this, in the very first week we talked about the equivalent norm theorem. but that was concerned with finite dimensional spaces. And actually this is sort of, once you have this, the proof of the equivalent norm theorem, it boils down to one line, but of course you rely on heavy prior results. So here, let's first read the statement. So if you have a vector space X, and you have two norms on it, in which X is a Banach space, okay? And of course for finite dimensional spaces you have this, because we proved finite dimensional spaces are complete. So now, as it so happens, if you have one inequality, say X in one norm cannot exceed the X in two norm, then you get the second one automatically for free. Right? So that simply means that if you have this one inequality on the norms, then they are automatically equivalent, because you get the second inequality for free. Right? So that's quite surprising. But, okay, how to prove it? Well, by assumption, the identity map I from X equipped with the 2 norm to X equipped with the, well, maybe I shouldn't say 2 norm, but that norm indexed by 2 is an isomorphism. Banach space isomorphism, that is, by assumption. And why is this? Well, maybe in yellow. So if you look at Ix acting on element X in the second space, and you look at its norm in the one space, right, because it maps to the one space, then this is what? Well, by definition of the identity, well, it's just going to map the element to itself, so that's going to be this. But now you use this assumption. This assumption says that there is constant C1, so that this is at most C1 times X in 2 norm. Yeah, but if you read this here, at most being equal to that, and that being valid for all X in, well, this guy here, then this just means that the identity map is bounded, right? So of course identity map is clearly bijective, it is also linear, and that's why you have an isomorphism, right? Yeah, but if you have this isomorphism, then the inverse mapping theorem tells you that the inverse map is continuous, aka bounded, right? So it's inverse. And what's the inverse? No, yeah, I minus 1, which goes the other way, but which has the same action. So from 1 to 2 is bounded by the inverse mapping theorem. Okay, this shows so if you look at I minus 1 now acting on X and this being in 2 norm, then by definition this is just this, and since it is bounded, there exists C2 that this guy is less than or equal C2 times X in the 1 norm, right? And there you have it. This green underlined thing is exactly the second one that I claim up there. All right, and this works for all X in yellow double star. For all X in, let's move this a little bit to the left here. For all X in yellow double star. All right. Okay, and that's that. So these two norms are automatically equivalent. From once you have one inequality, you get the second one for free if you are in Banach space. All right, good. Now, to prepare for the last big result in this section, so the last big consequence of the bare category theorem, we need some further terminology that is not so far-fetched. After all, this is more or less how the Cartesian products work, Rn or Cn, the coordinate spaces. So what goes on here is as follows. Start with a countable index set, and a collection of normed linear spaces indexed by a member of the index set, right? So each one comes with its own norm. That's why I index the norm with alpha. And now what you do is you look at essentially the Cartesian product. So that's what's written here. So I take, well, I could enumerate them, x alpha 1 cross x alpha 2 cross all the way till the last one, right? It might be infinity, right? So, but anyways. Okay, then maybe I will erase this cross, because if it is infinity. All right, and capital X, so that is the Cartesian product of all those x alphas, and the element is going to be written, well, no surprise here, as this, right? So if I is the index that is finite, that's just going to be an n-fold copy of your capital X, you know, alpha. And the elements in there all have to satisfy this little constraint, which is also not so far-fetched. Right, then the claim is this new, it's a vector space if you define the operations component-wise, right? So if you have two of these guys, two of those x alphas, you add them together, what you will do is you will add them component-wise. That's how the vector space structure is defined. And then as it turns out, this vector space is a normed linear space with this norm down here. That's probably easy to see. You have to check, well, non-negativity of the norm, but since you take here a sum of non-negative terms, because each one of these guys is a norm, that's only going to be 0 if the x alphas are all 0. Scalars you can pull out because you take a sum of norms itself. And the triangle inequality is also true because each one of those guys, of those alpha norms, satisfies the triangle inequality. So this is, I would say, clearly a normed linear space. And it's called the direct sum of the spaces x alpha, and typically it gets this little abbreviation symbol here. All right, so this is a circle with a plus in it. You might have seen this notation in linear algebra. Okay, more is true. This thing here is a normed linear space, but also if all those x alphas, if all those normed linear spaces up there are complete, aka when they are Banach spaces, then the whole yellow box here, the direct sum, is also going to be a Banach space. We discussed in the exercises some time ago the direct sum of Hilbert spaces. This is very much the same thing. Well, up to the fact that in Hilbert spaces, of course, you have inner products, which you don't have here in those general direct sums. All right, that's of course a fundamental difference. But the Hilbert space direct sum is a special case of this yellow box. That's more precise. Okay. All right. Good. That is this. Now the next concept is something that we already encountered when we discussed Hilbert spaces, because there we discussed the projection lemma. Right. This was a major building block in the proof of the Riesz representation theorem. So you have a closed subspace in a Hilbert space, and then, well, you can add to it in a sense the orthogonal complement, and that lets you decompose the whole Hilbert space into a sum of these two spaces. And that's precisely what's paraphrased here in general terms. So if you have a vector space capital X and two subspaces, not necessarily closed, then we call them complementary if, well, they add up to all of it, and you can represent each vector uniquely as a sum of two vectors x1, x2, x1 being in capital X1 and x2 being in capital X2. And the fact that you can do this uniquely is encoded in this little constraint. All right. So the projection lemma yields a particular incidence of complementary subspaces. Okay. Right. So that's what's written here. Equivalently, this yellow star means you can decompose each vector in the big space X as a sum of something in the subspace X1 and something in the subspace X2. All right, and you can call then the one subspace complementary to the other one, or the complement to the other one. That's just terminology. All right. Now, what's the point of this? Well, it prepares something. So first, small corollary. So if you have a Banach space and you have two complementary subspaces, so that means X decomposes in, well, this fashion. All right. And each of these guys here is closed. That's what you have in the projection lemma in Hilbert spaces, right? You start with a closed subspace and then you can complement it by the orthogonal complement, and that's always closed. That we discussed a long time ago. All right, then what happens is there exists a delta such that you have this curious double inequality for the norms. All right. Now, the first part here, this one is absolutely trivial because that's just a triangle inequality for this norm in the Banach space, right? Now, the triangle inequality gives you also a lower triangle inequality. Let me write it here, which goes with this minus and which goes here with this absolute value outside. Yeah, but notice here, this is much better. This claims here you have up to this constant here, which in general not 1, you have a plus sign there. So this is a much stronger, lower inequality than what you would get from the ordinary triangle inequality. This here, the upper end is ordinary triangle inequality. The lower end is much better than that. All right. So in equivalent terms, if you remember the norm on the direct sum, the norm on the direct sum here would just be, no, let's use a color, would just be well, if you have x and this cross is the direct sum norm, then this is just because x is x1 plus x2, because they're complementary, it is x1 plus x2 in norm, right? So, and then this yellow box up there just says that the direct sum norm on the direct sum of those Banach spaces is equivalent to the initial norm. Right? Remember, the subspaces, because they are closed, they are Banach spaces. All right. So now let's prove this, and this will prepare then the final big theorem in this section. Proof. So if T goes from the direct sum to just X is defined by, so the elements in the direct sum, these are these pairs. Remember the definition, x1, x2. And what I'm going to do is I'm just going to sum up sort of their coordinates. Yeah, that's what it does. Then T is linear. That is no further, needs no further justification. And T of x1, x2. Well, so that's the trivial part. That's just the ordinary triangle inequality in x, x1 plus x2. Right. Okay, and this here, remember, this is precisely what I wrote here in yellow. This is, of course, the direct sum norm of the pair x1, x2. So here's a cross. Okay, so this shows that T is a bounded linear transformation from the direct sum of x1, x2 to the space x, right? That's precisely, if you read this here being at most equal to that, with this map, that's precisely what it says, right? That it's a bounded linear transformation between, in the way it is written there, all right? Good. Now, having this, clearly, T is injective and surjective. Why is this? This is because these are complementary subspaces. Since X, J are complementary. Right, so we can maybe here in yellow. So injectivity, if this is mapped to 0, then this just means that x1 plus x2 maps to 0, right, is equal to 0. Yeah, but that means x1 is minus x2, and now you're in the case that the guy on the left is in capital X1, right? And the guy in the right, because it's a subspace, is in x2. So these two elements are in the intersection, but since these are complementary subspaces, the intersection is the 0 vector space. So that's why x1 equals x2 equals the 0 vector. So it's clearly injective. And it is also surjective because of the complementary thing. Any vector x in here you can uniquely decompose in this fashion. So clearly it is in the image of that pair x1, x2 under the map T. All right? So that's true. So T is a bijection. And we already showed that it is a bounded bijection. So now you use the inverse mapping theorem, right? By the inverse mapping theorem, this guy, t minus 1 from x into the direct sum is bounded. So let's just write out what this means. So t minus 1x, this is now going to be an element here in the direct sum. So I use the cross, almost looks like an x, but okay, in the notes it's clearly visible that it's not an x. This is less than or equal to c times x, all right, for all x in x. Good, and now you just write this out, what it means. Since the xj are complementary, this implies, remember the x here in this inequality down there is of the form x1 plus x2. So this thing here, maybe I can write this here. This will just be the x1, x2 and the direct sum norm of this, and this is by definition x1 plus x2, right? And then you use also here x1 plus x2, and you have what you want. So I will copy this now and write it here. This implies x1 plus x2 less than or equal to, well, let's write all the steps that I already wrote in yellow on the previous slide with the cross, less than or equal to c x1 plus x2. And then you would just divide by c, bring this here, then you got the statement of the theorem with delta equals to 1 over c. All right, this completes the proof. All right, excellent, very, very nice. So now we have one outstanding theorem, which is the closed graph theorem. That's also very impressive. And then after that, okay, there's a corollary. That's actually useful if you ever study quantum mechanics from a mathematical viewpoint. And then once done, then we will move to the next subsection. Okay, I hope I see you soon.